Okay, folks, today we're going to talk about moment of inertia. To understand moment of inertia, let's look at the words. Let's start with inertia. Inertia is a resistance to acceleration. You'll learn all about this in dynamics. The resistance to acceleration is mass. You should have learned in physics, if you took it, that F equals ma. And this mass is what we call inertia. So for a given force, if the mass is high, the acceleration is low. So lots of mass will resist acceleration. And so mass is resistance to acceleration. Ah! Sorry about screaming, but one of the students asked me to just scream out of nowhere. So let's continue this discussion. Speaking of resistance to acceleration, I need to tell you about a job site in Kenya we were on with Engineers Without Borders. So, XD, I don't know how to say this, but it was really hot and nobody wanted to work. And one of the students says, everyone seems to have a severe case of laziness. I said, laziness? What is laziness? And laziness was just his code word for laziness. So the moment of inertia, now that we've said what inertia is the moment of the mass. And it's not the first moment, it's the second moment. Mass times distance, that would be the first moment. And this is the second moment because we're taking x squared dm. And this is called the mass moment of inertia. And it's the resistance to angular acceleration or spinning acceleration. You'll learn all about this in dynamics next semester. But for now, what we want to talk about is area moment of inertia. I'm being a bit too loquacious, so let's just go to what the definition is. So this is the definition of moment of inertia. And really we should say area moment of inertia, because in these integrals, instead of dm, we're using dA. So integral y squared dA and integral x squared dA. So an interesting thing I want to point out is that Ix is integral y squared dA and Iy is integral x squared dA. It seems a bit backwards until you realize that the y distance, let me just draw a potato here. The y distance of a piece of area, okay, the y distance is the distance from the x-axis, right? You measure y from the x-axis. So you can think of I about the x-axis is integral y squared dA. Now, I don't know why we always use potatoes when we do a generic shape. Sometimes I wonder, why couldn't we use some kind of carnivore, like a T-Rex? So why don't we do that? So here's a T-Rex. He's probably the alpha carnivore of all time. But anyway, if you were to take a small piece of this carnivore and measure its x distance, it is measured from the y-axis. So I, about the y-axis, the integral x squared dA, because it's the distance from the y-axis. That's why you have this cross. Integral y squared dA is ix, and integral x squared dA is iy. And lastly, the polar moment of inertia, J, is integral r squared dA, but from Pythagorean's theorem, r squared is just x squared plus y squared dA, and so that's integral x squared dA, which is iy, and integral y squared dA, which is ix. So if you just add ix and iy, you get the polar moment of inertia, J. So here's a way to remember what this means. Remember when we did integral x dA, and we divided by integral dA, it was the average x. Well, we're not dividing by integral dA, but instead of doing x dA, we're doing x squared dA, and instead of integral y dA, we're doing integral y squared dA. And the difference between x and x squared, other than it's a lot bigger, is that when you square a number, let's say minus 2 or plus 2, that both comes out to positive 4. So the integral of something squared dA always gives the positive. It doesn't matter if it's plus or minus, the x squared will be positive, or the y squared will be positive. So a way to think of this is that the integral of y squared dA is sort of a measure of how far away from the x-axis your area is. That's why it's ix. And integral x squared dA is how far away from the y-axis you are. Plus or minus doesn't matter because you're squaring it. And so a good feel for ix is a measure of how far away the area is from the center or from where you're measuring this, and iy is how far away in the x distance you are in terms of area. And finally, r squared dA is a measure of how far of a radius you are from a spot when you integrate that. So how much of the area is far away from the center. So the question is when you do these integrals of x squared dA, y squared dA, or r squared dA, where are you measuring x, y, and r from? You need to have a coordinate system put somewhere. And so you have to have a point that you're measuring everything from, and we've been calling this point Bill, Wyoming. Typically, you set the coordinate system at the centroid, which we learned in the Chapter 9 lectures how to do. So you do Chapter 9, you find the centroid, then you measure x squared, y squared, and r squared from the centroid. Put Bill, Wyoming at the centroid of your area. For those of you who are just joining us, I've been making a joke that the coordinate system is measured from Bill, Wyoming, which is a town in Wyoming with a population of 2, Bill and his wife, because one of my students said, I live 25 miles northeast of Bill, and I knew what he was saying because I knew where Bill was. The fact that this student had to use Bill as a point of reference or the origin said how small of a town he was from. So if you were to drive, let's say, a snowmobile from Bill to Clariton, it would have to go like this. And you would drive there. And you would be measuring your distance, let's say 25 miles, from Bill to wherever you were. What I'm saying for this class is that we are putting our coordinate system not at Bill, Wyoming, but at the centroid of the area. Let's compare the moment of inertia to the centroid. To calculate the centroid, we had to do the integral x dA, and to calculate the moment of inertia, we had to do the integral x squared dA. So we're comparing x dA with integral x squared dA? Well, if we put our centroid, Bill, if we put Bill, the coordinate system centroid, Hergefuger. Let me try that again. If we put our coordinate system origin Bill at the centroid of the area, okay, so for this rectangle right at the middle, and then we did the integral x dA, Squirtle. The integral of x dA when the coordinate system is at the centroid is 0. The integral of y dA is 0. That's the definition of the centroid, that there's no moment about the centroid. However, the integral of x squared dA is most certainly not 0. At the centroid, it's never 0 because it's x squared. The positives and negatives don't cancel out. However, the moment of inertia is minimum at the centroid, but it's not 0. So to summarize, to get the moment of inertia for a given shape, let's say about the x-axis integral y squared dA, and that's I0x, and I0y, the integral about the y-axis is x squared dA when x is measured from the centroid.